Hello and welcome to Anton Math. Now in this section we're going to just briefly be going over matrices and some of the basic properties of matrices and what we can do with matrices. Now I'm not going to go real deep into this subject material. I really only need the basic stuff, so this isn't really going to be sufficient for a linear algebra course or anything like that. But we're going to get to the point that we're going to be able to use matrices in our next section, elementary number theory, in order to help us kind of expedite the processes that we're going to have there. And when we get there, you'll see how useful this can be. But to talk about matrices, first I need to talk about what are called vectors. Now in geometry and physics, we think of vectors as a directed line segment, but here we're going to be a little bit more simple with it. Now a vector is an ordered finite set of numbers. And we're going to say real vector if all of the elements of the vector are real numbers, integer vector if they're all integers, and so on. And if it's required that all the elements belong to the same number set, those numbers are going to be called scalars for those vectors. So we could have an integer vector where we're only talking about integers in this space where the only elements of our vectors are integers and all the scalars are integers. Now, if we have a vector, the number of elements in the vector is called its dimension or its length. And we say the set of all real vectors of length n is denoted r to the n. So this double barred real numbers r to the n. And really when we say r to the n, what we mean is the cross product r, etc. n times, right? N different real number sets crossed with each other. So you can think of all of these vectors, in a way you can think of them as n tuples. And that's exactly what we're talking about. We're talking about ordered sets of n elements. Now we have a couple of these that we're familiar with. R squared, this is our typical Euclidean plane that we do graphs on and things like that. R cubed, this is all of the real points in 3 dimensions, and etc. And we usually call the elements of a vector V entries. Now I've bolded this, but it didn't show up really well. We can either write a vector when we use when we're indicating something to be a vector, usually we'll bold that, and we'll usually use V or U or W, but usually we use a bold V, or we'll use a V with this little kind of arrow on top. So I'll be kind of interchanging between the two of them. So if the letter is bold, then that means a vector. If it has this little kind of half arrow on top, that also means it's a vector. Now we call the elements of a vector V entries, and we would usually write something like the vector V equals, V1, V2, all the way to Vm, however many entries it has. This is how we would indicate a general vector V of length m. And if we have two vectors, we're going to say that the vector u equals the vector v if and only if each of these entries are equal component-wise. So ui equals vi for every I. So of course they need to be the same length for us to even be able to talk about all of the entries being equal. But we'll say that the two vectors u and v are equal if and only if each of the entries are equal to each other. So we can have an example of this. We could have something like, let's say I have two vectors. This is just a little side example, kind of a bookish example. Let's say I have these two vectors x3, and I know that x3 equals the vector 4 x plus y. Well, then we can solve for x plus y. If these vectors are equal, that means each of their components are equal, or each of their entries are equal. So x is going to be equal to 4, because these first entries are both equal. And if x is 4, well, then x plus y is 3, so y is going to be -1. Okay. Now, we have operations on these vectors. Let's start with the two most basic operations. Addition and scalar multiplication. Now, for addition to be defined, both vectors must be the same length. But let's say I have two vectors the same length, then I have that the vector u plus the vector v. Now all I'm going to be doing here is I'm going to be adding each of the entries of u and v component-wise. So my first entry in u plus v is the first entry in u plus the first entry in v. The second entry in u plus v is the second entry of u plus the second entry of v, etc. All the way to, let's say they're both size n, is going to be un plus vn. So again, they both need to be the same length, of course, and all we're doing is just adding the entries together component-wise. Now, if k is a scalar, we can talk about what's called scalar multiplication. And what this is if I have some vector v, we'll say v is a vector of size n, then the scalar k, which is just a number, multiplied by the vector v, is going to be, we're basically just distributing k to each of the entries. So I'm just going to multiply k through to each of these entries, v1, v2, and so on. Okay, so these are our two basic vector operations, addition and scalar multiplication. Now we can kind of multiply two vectors, but it's a little bit different, and we'll talk about that in a moment. First, a couple of properties for these operations. Addition is commutative, right? And we know commutative means that u plus v is equal to v plus u. Addition is associative, so if I have some vector, let's say t, I can say t plus and then this sum u plus v. That's the same thing as t plus u first, and then adding v. Or we'd usually just write this without any parentheses at all because it's associative. This is just t plus u plus v. And this makes sense. Both of these make sense, right? Because of how we've defined addition. If I'm just adding the entries together, well, that's going to be the same whether I list u first or v first. And it's going to be the same no matter which order I add the entries in these three vectors. Now, scalar multiplication is also associative. So that just means if I have two scalars a and b, that's going to be a times the vector, or sorry, times the scalar b times the vector b. That's the same as multiplying AB first, and then taking this new scalar AB and multiplying that through the vector V. It's the same no matter which way you do it. Scalar multiplication is distributive, and what that means is if I have some scalar A multiplied by the sum of the two vectors u plus v, I should say it's distributive over vector addition. Now I can just distribute this A. This is the same as the scalar A times u plus the scalar A times v. And we have additive inverses and identity. And what that means is if I take a vector v and I add to that the same vector v multiplied by the scalar -1, these two vectors are additive inverses and give me the additive identity, which is this 0 vector. Now the 0 vector, as you would expect, is just the vector where all of the entries are 0. And we have 0 vectors of every size. Okay, so these are our basic operations. Now let's take a look at our multiplication, or would-be multiplication. We actually call it the dot product. Now the dot product, if I have these two vectors u and v, again u and v need to be the same size. I'm going to have the vector u dot the vector v. This is defined as the sum of the products of the components. So let's say these are both size n vectors. I'm going to go I from 1 to n. ui times vi, and then add all those together. So in other words, I'm just taking u1, multiplying that to v1, and then adding u2 multiplied to v2, etc., until I get un multiplied to vn. Now you'll notice where with scalar addition, or with vector addition and vector or scalar multiplication to a vector, we started with vectors and we ended with vectors. The dot product's a little bit different because we're going to start with two vectors and we're going to end with a scalar, right? These are just the entries and then summed. This isn't a vector. I haven't put any parentheses here. This is just going to be a number or a scalar. All right, now let's look at an example of all of these, a quick example. Let's say I have these three vectors t. We'll say t is equal to 1, 2, 3. Let's have a vector u equal to -1, 3, 0, and a vector v, say that's equal to 2, -2, 2. So I can talk about u dot v. So u dot v from our dot product up above, I'm just going to be looking at each of these entries component-wise and then adding the products all together. So I'm going to multiply u1 times v1 gives me a -2 plus. Then multiplying u2 times v2 gives me a -6. And then u3 is 0, so u3 times v3 is 0, so I'm just going to get -8 for my dot product. So again, just a scalar, not a vector for my result for my dot product. Now we can combine some of these. Let's say I have the vector t minus the vector u and then that whole thing dotted with the vector v. Well, first of all, we didn't talk about vector subtraction, but vector subtraction is really just going to be the same thing as vector addition, but I'm multiplying the second vector by the scalar -1. So we're just going to multiply this by -1 and add them together, or you can think of it as subtracting the entries of u from the entries of t. So this is just going to be 1 minus -1 is 2, 2 minus 3 is -1, 3 minus 0 is 3, dotted with v, which is 2, -2, 2. And now we're doing our dot product, so our first product is 4, and then adding to that -1 times -2, which is 2, and adding to that 2 times 3, which is 6, gives us a grand total of 12. Okay, so these are vectors, vector operations, and in the next video we're going to generalize the idea of these vectors into what we call matrices. We'll see you there.